Welcome to Brain Vision.
Okay, so for this question, we can apply the energy balance equation. So we have E dot in is equal to E dot out, which is Q dot in plus M dot H1 is equal to M dot H2. Q dot in here is the rate of heat transfer due to the forced air. M dot here is the mass flow rate for the forced air, and H1 is the initial enthalpy for the forced air. H2 is the final enthalpy for the forced air. If we do some arrangement here, we have Q dot in is equal to M dot times H2 minus H1. So we know H2 minus H1 can be expressed as Cp times T2 minus T1. Cp is the specific heat of the air at constant pressure, and T2 is the final temperature for the air, and T1 is the initial temperature for the air. So we have Q dot in is equal to M dot times Cp, and then times T2 minus T1. So in this question, in order to determine the specific heat of air at constant pressure, we need to use the interpolation. Since there's no exact specific heat of the air at constant pressure for the temperature that was given from the questions. So first we need to determine the average temperature. So the average temperature is T1 plus T2 over 2, which is 30 plus 273 Kelvin plus 40 plus 273 Kelvin over 2, since the temperature range is between 30 degrees Celsius and 40 degrees Celsius. If we convert to Kelvin, we have something like this. So eventually we have the average temperature is about 308 Kelvin. So now we know if we take a look at the table A2, which is ideal gas specific heat of various common gases. So let's take a look at the air section. As you can tell, 308 Kelvin is lying between 300 Kelvin and the 350 Kelvin. So therefore, we know at 300 Kelvin, the corresponding specific heat at constant pressure for the air is 1.005 kJ per kilogram times Kelvin. And then at 350 Kelvin, the corresponding specific heat is 1.008 kJ per kilogram times Kelvin. So now we can use interpolation to figure out the specific heat for the air we need for this question. So eventually we'll have Cp is equal to 1.00548 kJ per kilogram times Kelvin. And we also know the mass flow rate can be equal to the density times the volume flow rate, which is equal to P1 over RT1 times V dot. P1 is the inlet pressure, R is the gas constant for the air, and T1 is the initial temperature for the air. And then we'll have Q dot in just simply equal to P1 over RT1 times V dot times Cp, and times T2 minus T1. So we know the initial pressure, or the inlet pressure, is given as 1 atmosphere, which is about 101.325 kilopascal. And we know the gas constant is 0.287 kJ per kilogram times Kelvin. And T1, which is the initial temperature, is 30 degrees Celsius, which is 303 Kelvin. And we know the final temperature is 40 degrees Celsius. And we know the volume flow rate is 0.3 meter cube per minute. If we convert it to meter cube per second, it's about 0.01 meter cube per second. And we know the specific heat is 1.00548 kJ per kilogram times degrees Celsius. So now let's plug in back to the equation to determine the rate of heat transfer due to the forced air, which is equal to P1, which is 101.325 kilopascal, and then multiplied by 0.01 meter cube per second, and then times the specific heat, which is 1.00548 kilojoule per kilogram times degree Celsius, and times the change in temperature, which is 40 degrees Celsius minus 30 degrees Celsius. And this whole thing here over the gas constant, which is 0.287 kilojoule per kilogram times degrees Celsius. I'm sorry, not degrees Celsius, times Kelvin. Okay, and then multiplied by the initial temperature in Kelvin form, which is 303 Kelvin. So in this case, we need to use 303 Kelvin, okay, because the gas constant is having a units times Kelvin here. So the reason why we can use the specific heat as a degree Celsius here, because there are two values for the temperature, which is 40 degrees Celsius and 30 degrees Celsius. So for the specific heat, we care more about the temperature change instead of the individual temperature. So that's why we can use degrees Celsius instead of Kelvin, because there's no difference. So we can also express as a specific heat in 1.005 kilojoule. I'm sorry, not kilojoule. 48 kilojoule per kilogram times Kelvin. Okay, because all we care about is the temperature change, and we know the temperature change between degrees Celsius and Kelvin is the same, and I can prove to you. So if we convert the temperature into Kelvin, so we have 40 plus 273 Kelvin minus 30 plus 273 Kelvin, and this is also equal to 10, but with the unit Kelvin. Okay, and when the 40 minus 30 is equal to 10 as well, but with the degree Celsius, since the unit for is degree Celsius. Okay, so therefore, as you can tell, the temperature change between the degree Celsius and the Kelvin is the same. So when you use the specific heats for a certain material, you can either with the unit degree Celsius or with the unit of Kelvin. Okay, but for the gas constant, it's different because gas constant is more targeting with the individual temperature. So since the gas constant is coming with a unit Kelvin, so we have to use the temperature in Kelvin form. Okay, so now this whole calculation here will give us the rate of heat transfer due to forced air is about 0.117 kilowatts, which is 117 watts, and we know the total rate of heat transfer can be equal to the rate of heat transfer due to the forced air plus the rate of heat transfer from the outer surface of the duct to the ambience. Let's say Q dot here. Okay, and this is Q total here. So therefore, we'll have the rate of heat transfer from the duct to the ambience is simply equal to the total rate of heat transfer minus the rate of heat transfer due to the forced air. And we know the total rate of heat transfer is given as 180 watts. And we know Q dot in, which is the rate of heat transfer due to the forced air, is about 117 watts. And this will give us the rate of heat transfer from the outer surface of the duct to the ambience is about 63 watts. And this is the answer for this question.